Phoenix, the evolution of pipeline simulation. Gregg Engineering's NextGen hydraulic simulator is an engine of truth, a verification system that continuously produces high-fidelity and operationally trusted results and outputs that the largest pipeline companies in North America rely on daily. While many external AI vendors are attempting to approximate pipeline behavior, Gregg Engineering already produces the authoritative representation of it. In an era where the value of intelligent systems is fundamentally determined by the quality of the data behind them, this realization is critical. The Phoenix modules represent a deliberate, responsible effort to extend the value of next-gen hydraulic simulation by building insight on top of that truth engine, without replacing physics, engineering judgment, or established workflows. Phoenix modules are used to generate and recommend optimized commercial and operational solutions based on the current pipeline state, scheduled outages, forecasted supplies and deliveries, nominations, and market conditions. These modules work in tandem with NextGen and will trigger hundreds or even thousands of steady-state or transient multi-scenario runs during processing, and use the results to steer the solutions during optimization. For solutions requiring heavy-duty processing power, multiple networked machines running NextGen can work in parallel and yield substantial speed increases. Reliable and time-tested next-gen hydraulic simulations are also used to validate all final Phoenix module results, to ensure that AI-based recommended operations are viable and will result in expected outcomes on the actual pipeline. Another use for NextGen is to generate pseudo-historical data for use in training AI systems. Many AI-based pipeline operational solutions rely on historical SCADA data to train the AI system. Phoenix modules can not only use historical data, but also use NextGen simulation results for training. NextGen can generate the equivalent of 20 years' worth of pseudo-historical data in just a few hours, but with a wider variety of operations than typical historical data. The Phoenix modules currently under development at Gregg Engineering are the Operational Optimization module, the Next-Day and Intraday Capacity Discovery module, the Path Portfolio Optimization module, and the Outage Scheduler module. Several additional Phoenix modules, such as the Phoenix AI-based Pipeline Simulator, are also planned. The goal in the Operational Optimization module is to minimize system-wide fuel consumption, or the greenhouse gas emissions resulting from fuel combustion, by recommending which compressor stations should be turned on or off, and how the operating set points at those stations should be set. The recommended solution and station operations can be a fixed operation when using steady-state simulations, or can change over time when using transient simulations. This module would typically be used for short-term, next-day operational guidance based on forecasted nominations or flows and scheduled outages, but could also be used for more long-term operational analysis. To quantify the benefit of the optimization, we can just use the total system fuel consumed, but also have the option of using varying fuel costs at different locations to calculate a total system operating cost in dollars. Another option is to activate emissions modeling in NextGen to calculate all emissions from fuel combustion and convert those to tons of CO2 equivalent emissions, and then apply varying carbon taxes and emission fees to calculate the total system-wide operating cost in dollars. Having a total dollar amount for comparison purposes and to quantify the benefits of any optimization is typically more useful for decision-making than just volumetric numbers. System capacities can vary widely depending on weather predictions, forecasted loads, nominations, scheduled outages, and the distribution pattern and timing of supplies and deliveries. The Phoenix Next-Day and Intraday Capacity Discovery module can calculate available capacity and identify pockets of unused capacity still available on a zone-by-zone basis, or with multiple from-to combinations and for either next-day or intraday time periods. For intrastate pipelines, profitability can depend on a combination of fixed transports and selected buy-sell paths, and the quantity on each path. Different paths and amounts on each path interact and affect the overall capacity of the system, and increasing the quantity in one path can easily wind up restricting other, more profitable path combinations. The Phoenix Path Portfolio Optimization module uses current market prices, hydraulic simulation runs, and optimization techniques to determine the most profitable portfolio of buy-sell paths and quantities that fit within the capacity of the system. A single scheduled maintenance task, PIG or inline tool run, or outage can reduce system capacity. Since the system capacity is already being reduced, why not schedule other outages and tasks to take place at the same time? The Phoenix Outage Scheduler module will use optimization techniques to schedule outages and maintenance tasks to minimize loss of capacity and the duration of capacity loss. The Phoenix AI-based pipeline simulator mimics the NextGen hydraulic simulator. While not as accurate as a true hydraulic simulator, it offers a pretty good approximation and is considerably faster. When NextGen performs optimization runs for operational or commercial goals using the Phoenix optimization modules, all runs are stored in an archive on a per-model basis. The AI-based pipeline simulator uses these archived hydraulic simulation results generated by NextGen to train and periodically retrain a series of neural nets that mimic NextGen simulation results. Using the very fast AI-based simulations for preprocessing in tandem with NextGen hydraulic simulations for validation can result in substantial reductions in execution time for Phoenix optimization modules that require thousands of simulations. The different Phoenix modules use a variety of optimization techniques to determine solutions. Genetic algorithms take an evolutionary type approach, where multiple batches of scenarios are run, and genetic algorithms create each successive generation of scenarios. Deep learning AI is also used, where results of simulations are fed into deep learning neural nets to detect trends and relationships, and then generate solutions. Finally, operating logic can also be used to steer solutions based on pipeline rules of thumb, operating experience, and in some cases, just plain common sense. Note that all of these optimization approaches require the ability to potentially perform hundreds or even thousands of steady-state or transient simulations very quickly, so that suggested pipeline operations can be confidently validated. Which brings us to our next slide and the Phoenix NextGen architecture. Phoenix modules typically reside on a primary computer and communicate and transfer data with NextGen through databases and Excel spreadsheets. A standard session of NextGen can work with the Phoenix modules, but can oftentimes get bogged down when hundreds or even thousands of runs need to be made during optimization processes. Performance typically peaks with between 4 and 8 run engines running in parallel, regardless of how powerful the machine is. For this reason, Gregg Engineering developers created a special MSR server application that Simulation Office can boot up as needed when Phoenix modules need to crank out runs. Each MSR server will launch up to 8 run engines, and multiple MSR servers can run on a single machine, depending on the number of cores available. This distributes the processing load so that no one application becomes overwhelmed, and we can now properly take advantage of high core count machines. For example, with a high core count machine, you could potentially have 4 MSR servers with 8 run engines each, for a total of 32 run engines running 32 simulations in parallel. Additional machine-to-machine communication protocols have been built for Phoenix so that additional network-connected machines can participate in running simulations in parallel. There will always be a single primary machine that hosts the Phoenix modules, but any number of secondary machines can help out to perform simulation runs, and the more machines that participate, the faster results can be generated. In this slide, we can see that when the Phoenix Operational Optimization module launches a multi-scenario run with several hundred transient scenarios, each participating machine will take on a subset of the scenarios. Depending on the size of the subset and core count of the machine, several MSR servers will be launched on each machine, and each MSR server will launch its own set of run engines. In this example, we have over 100 run engines running transient 24-hour simulations in parallel. Having this kind of parallel processing architecture available under Phoenix and NextGen means that optimization processes that might have taken several hours or even days can now be completed in a much more reasonable time frame, which also means that operational and commercial decision makers have the answers they need when they need them. The Phoenix modules represent a deliberate, responsible effort to extend the value of hydraulic simulation without replacing physics, engineering judgment, or established workflows. The Phoenix initiative actually has its roots way back in 2012 with the genetic algorithms and neural nets developed by Gregg Engineering for its Flowdesk optimization program. This work was restarted in 2024 to function on top of the NextGen application suite with newer optimization technology, transient simulation support, and parallel processing features. The first Phoenix steady-state and transient optimization modules are expected to be released in late summer 2026. If you have any questions or would like additional information on the Phoenix modules or any other Gregg Engineering pipeline simulation product, please give us a call.